Hello, this is the second part of the chapter 6.4, and we'll talk about process of Gram-Schmidt orthogonalization in two-dimensional space. Okay, let's look at examples. We have a space W spanned by two vectors x1 and x2, and those vectors are given us explicitly. They are not orthogonal, so we want to construct an orthogonal basis of two vectors. Let's call them v1 and v2. And again, it's easier to start just looking at the graphical representation of our vectors. So we sketch here a vector x1 and x2. And let's start the Gram-Schmidt orthogonalization process. And the first step is very lovely and simple. We take our vector x1 and we proclaim it to be our first orthogonal vector, v1. So we just basically change names here. Okay, so what is step 2? We want to create the second vector, v2, which is orthogonal to our vector v1 or x1. So we can use a projection of our vector x2 into the vector x1. Or, since we just changed the notation here, we are actually looking at the projection x2 to newly developed vector v1. And we'll call this projection P. Okay, so when we can have a projection, we also can find its orthogonal component v, which exactly our vector v2, which just a difference between our vector x2 and its projection P. And we can calculate it using our projection formula, which we studied in the previous several chapters. Okay, so we now can substitute our vectors x1 and x2 and calculate our orthogonal vector. So the first component is our vector x2, which became x1, which became v1. 15 is our new dot product in the numerator. 45 is a dot product in denominator, and it's all multiplied by the vector x1. Okay, so we conduct a little bit of algebra, calculate, and get the vector 0, 0, 2, which is exactly what we have here. Our x2 have only the z component. So we can stop here because we only have two-dimensional space, R2. So our Gram-Schmidt process have only two steps. We only looking for two orthogonal vectors. So we can use our vectors v1 and v2 and report them. And we can just say v1 and v2, or we can put actually number. Our first vector v1 is exactly the same as our x1, and the second vector v2, we just calculated it. And those vectors are orthogonal, and I strongly recommend you to calculate the dot product to confirm that indeed those are orthogonal vectors. Okay, that's a rather simple example, and in the next part, we will look at a little bit more complicated case.